Welcome back to the concluding part of the course on statistical thermodynamics. In the previous lecture, we revisited some of the concepts with which we started. We understood molecular partition function. We also understood canonical partition function. We understood the significance of first starting with non-interacting systems and then switching over to interacting systems. We also talked about the ensembles. And then we talked about connection of canonical partition function with the molecular partition function. Various equations which connect internal energy or entropy are here. U is equal to U naught minus 1 by Q del Q by del beta at constant V or del log Q by del beta at constant volume. And then this is a general equation, not specifically applicable to monatomic gas. General equation that S can be connected to canonical partition function. But then we have to be careful to decide the relationship between Q and Q. That is, whether you want to use Q is equal to Q raised to the power n or you want to use Q is equal to Q raised to the power n by n factorial. And later on, we can extend this equation to derive another equation for entropy of a monatomic gas, and that you remember we called as Sackur-Tetrode equation. That is different, but this is the general expression for the entropy, connecting entropy with internal energy and canonical partition function. The relation of internal energy with canonical partition function is also given in this slide. We kept on further developing more relations. For example, connection of canonical partition function with Helmholtz free energy, which was A minus A0 is equal to minus kT log Q. Very important relation for Gibbs free energy. Gibbs free energy is one of the most important thermodynamic quantity in chemical or statistical thermodynamics. Why I say Gibbs free energy is one of the most important thermodynamic quantities? Because whenever we say criteria of spontaneity, the first thing that comes to mind is that the reaction will proceed in the direction in which the Gibbs free energy decreases. And it will come to an equilibrium where delta G becomes 0 at constant temperature and pressure. And that is why this expression for Gibbs free energy becomes very, very important. Later on, we connected canonical partition function with enthalpy and pressure. Almost all thermodynamic quantities now have been connected with the canonical partition function. And we have already discussed how to recover molecular partition function from canonical partition function. Then in order to simplify the processes, simplify the equations, we thought that let us first of all consider only perfect gases. We know the differences between perfect gases and real gases. In perfect gases, no intermolecular interaction. In real gases, deviation from ideality, and that deviation from ideality comes due to onset of intermolecular interaction. So for gases, we derived this equation, G minus G0 is equal to minus nRT log n, or you consume n and convert G to Gm. We also invoked standard state condition. The advantage of invoking standard state condition with Gibbs free energy is that you can then later on connect this with delta G naught is equal to minus RT log K. That is the advantage of connecting G with the standard state condition. Let me again briefly tell what is the standard state. Standard state means the substance should be pure, pressure should be 1 bar, temperature can be any. All right. Translational contribution to partition function we already discussed in the previous lecture. But when the molecule is a diatomic, if the molecule is monatomic, it will have only translational degree of freedom. It may also have electronic contribution, but usually the electronic energy levels are far separated. So, therefore, that contribution is nearly 1. Once you deal with the diatomic or triatomic or polyatomic molecule, now you will have translational contributional, rotational contribution, vibrational contribution, electronic contribution. We discussed that for rotational contribution, you can deal with linear rotor, you can deal with non-linear rotor. For linear rotor, we derived this expression QR is equal to KT by sigma HCB. Sigma is the symmetry number, K is constant, Boltzmann constant, H is constant, Planck's constant, C is constant, speed of light. That means you have this rotational constant B. B is H cross by 4 pi Ci and T is temperature. We also brought in the importance of rotational temperature, that this equation is valid if the temperature is higher than rotational temperature. So, this was the expression for a linear rotor. But the molecule, for example, if it is a triatomic molecule, then the triatomic molecule can also be non-linear. For example, you have water, you have HDO. These are non-linear molecules. So, if the molecules is non-linear, then we discussed that the molecular partition function takes up this form. QR is equal to 1 by sigma into KT by HC raised to the power 3 by 2 into pi by ABC square root. Here A, B, C are rotational constants for the rotation of molecule in 3 dimensions. The significance of symmetry number cannot be ignored, and the symmetry number of several molecules, at least 4 molecules, are given over here. So, we knew how to evaluate, how to calculate the rotational contribution. If you carefully examine this equation, K is constant, H is constant, sigma is constant for a molecule, C is constant, and if you fix constant temperature, pi is constant, that means rotational contribution will depend upon A, B, C. And what is B? B is H cross by 4 pi Ci. I is equal to mu r square. That means you need the bond length and you need the reduced mass. With that kind of information, you can calculate the rotational contribution. After rotational contribution, we started discussing vibrational contribution, because when you go beyond atom, you have molecule, molecules. In molecule, the atoms can vibrate also around their bond. We talked about how many normal modes of vibration are there. For a nonlinear molecule, we discussed that if there are n atoms, then 3n minus 6 independent modes of vibration, and 3n minus 5 independent vibrational modes if the molecule is linear. As we talked earlier, that the overall partition function is multiplicative. That means if there are several normal modes of vibration, then the vibrational partition function is equal to the vibrational contribution due to first normal mode into vibrational contribution due to second normal mode into so on. So, overall QV will be equal to QV1 into QV2 into QV3 and so on. All right. To derive an expression for vibrational contribution to partition function, we took a very simple case. And what was that simple case? Is to take uniform ladder of energy levels. Look into this diagram. This is a uniform ladder of energy level. What is that uniform ladder of energy level? Is the energy separation between two states is constant. And then in that case, the QV turns out to be equal to 1 over 1 minus exponential minus beta Hc nu bar. Beta is 1 over kT. In terms of energy orders amongst translational, rotational, vibrational, electronic, the order is like this. First translational, then the next higher is rotational, the next higher is vibrational, the next higher is electronic. This is also going to be the order of temperature to achieve excitation for translational, rotational, vibration, electronic. Under normal conditions of temperature, the energy is not sufficient to excite the molecules, particles to higher or upper vibrational levels. If most of the molecules are in the ground state of the vibration, in that case your vibrational contribution to partition function usually will be very close to 1. All right. Keeping this in mind and also recognizing that there is a temperature called characteristic vibrational temperature, the partition function can also be expressed in terms of characteristic vibrational temperature provided the temperature is high. Okay. Then this is another elaboration of the statement that the overall partition function is multiplicative. Here you have first normal mode, which is the number is 1.00019. For second mode, the molecular partition function, the number is 1.09830, but this is doubly degenerate. Third one, 1.00306. The overall vibrational partition function will be first one into second one, and since second degeneracy is 2, it will appear twice, but in a multiplicative mode. Then you have the third one, overall value is 1.210. Still you see the value of the vibrational contribution to partition function is close to 1 only. That means not many molecules, particles, they are excited to upper vibrational states under normal temperature conditions. And since we discussed that the next higher energy level, the separation is electronic. So therefore, if I expand this, I have Q electronic is equal to G0 plus G1 exponential minus beta E1 plus so on. And since these values are very high, usually the electronic contribution to partition function is equal to degeneracy of the ground state. Keep that in mind. Now, overall partition function. Overall Q is equal to Q translational, Q rotational, Q vibrational, Q electronic. And when you substitute their expressions, you will have either this, or if you want to express in terms of characteristic rotational and vibrational temperature, you have another one. So that means whenever you are dealing with a certain problem in which the molecule has all degrees of freedom, translational degree of freedom, rotational degree of freedom, vibrational degree of freedom, electronic degree of freedom, you will need to know the overall partition function. Therefore, you will need to evaluate Qt, Qr, Qv, Qe. While evaluating Qr, you need to know whether the rotor is linear or it is non-linear, because the expressions for linear rotor and non-linear rotor partition function is different. Then further, we connected the molecular partition function with the mean energy. Translational contribution for one dimension was 1 by 2 kT, and for a molecule free to move in 3 dimensions it was 3 by 2 kT. If the temperature is not high, the rotational contribution to mean energy turned out to be a complicated expression, but if the temperature is very high, we find out it is equal to kT. For vibration, simply, if the temperature is very high, then it is equal to kT. Otherwise, at other temperatures, we derived another equation where mean vibrational energy can be evaluated. This is in the high temperature limit. Once you have information on mean energy and internal energy are correlated with each other. N times mean energy is equal to total energy, and total energy E is connected to U as U minus U0, and CV is connected to U, that means CV is connected to E. Here you can see that. And since beta is equal to 1 by kT, if you have any derivative with respect to temperature, you can further transform it to another equation where the expression is derivative with respect to beta. So therefore, you can use this expression or you can use this expression to obtain heat capacity. With several considerations to translation, rotation, vibration, electronic, we came up with an expression which could be used to estimate the constant molar volume heat capacity. This was a very important observation that when the temperature, let us say for a gas, you consider a gas. In gas, the molecules, gas molecules will always have translational degree of freedom. That means 3 by 2 R contribution will always be there. And if it is a linear rotor, you keep on increasing the temperature, another R contribution will come. If you further keep on increasing, then another R contribution come for a diatomic molecule. And if you consider diatomic molecule and you further keep on increasing temperature, then diatomic molecule will undergo dissociation. And once diatomic molecule undergo dissociation, diatomic means 2 atoms will convert diatomic, in the sense diatomic molecule will be like X2 will dissociate to 2X, and you will have 2 times translational contribution, because atoms will have only translational contribution. Finally, having discussed all other thermodynamic quantities, we ended up by connecting molecular partition function with equilibrium constant. Remember that equilibrium constant is very important thermodynamic quantity because it tells us how much product is formed. Not only academically, but industrially also it is a very important thermodynamic quantity. We established this relation of equilibrium constant with the molecular partition function and delta E naught, which is the difference in the 0 point energies. That means in order to evaluate equilibrium constant, what information do we need to have? We need to know the molecular partition function. And this molecular partition function is product of translation, rotation, vibration and electronic. We also need to know what is the value of delta E naught, that is the difference in 0 point energies. After connecting to K, the equilibrium constant, as I said that equilibrium constant is one of the remarkable thermodynamic quantities, because if I go back, you have equilibrium constant connected to delta G naught is equal to minus RT log K. Another very important thermodynamic relation, delta log K delta T at constant pressure is delta Vent half H naught by RT square. we realize the significance of equilibrium constant here. Once we have knowledge about equilibrium constant, we can talk about spontaneity of the process. And once we have equilibrium constant as a function of temperature, we can get enthalpy change of the reaction. That is the beauty of thermodynamics, that sometimes without doing experiments, you can even calculate the things. So here, the equilibrium constant that I mentioned, this equilibrium constant, it can be determined by calorimetric methods, it can be determined by spectroscopic methods. So that means this highlights that even if we get the equilibrium constant by means of spectroscopy, we can get enthalpy change. Enthalpy change, a property which is usually determined from calorimetry. After equilibrium constant, up to that point we were dealing with the ideal systems. Now how to deal with non-ideal systems? Because majority of the things are non-ideal. Ideality only arises under special conditions. For example, when we talk about the gases start behaving ideal when the pressure is very, very low, because then the molecules are very far apart from each other. And we know that the real gases, they differ from the ideal gases, because in the real gases there is onset of intermolecular interactions. There what we did was we introduced virial coefficients. The equation of state called virial equation of state was PVm by RT is equal to 1 plus B by M plus C by Vm square, etc., where B is the second virial coefficient, C is the third virial coefficient, and these virial coefficients have information about intermolecular interactions. You can compare, remember, ideal gas equation PV is equal to nRT versus van der Waals equation. In van der Waals equation, you brought in A and B, which correspond to attraction and repulsion representations. So similarly here, the virial coefficient B, virial coefficient C, these are indicators of intermolecular interactions or the deviations from ideality. Most of the discussion that we had was based upon Maxwell-Boltzmann distribution. We extended the discussion and brought in compartmentalization to give another angle to our discussion and derived the Bose-Einstein distribution function. The treatment was similar, but the final result, although looks nearly similar, but differs slightly. In the treatment of Bose-Einstein distribution function, we did not put any restriction of Pauli exclusion principle. Restriction of Pauli exclusion principle was introduced in Fermi-Dirac distribution, where we did not put more than 2 particles, more than 2 electrons in the same cell. Here also the treatment, the final look of the equation is nearly the same as that for the Maxwell-Boltzmann or Bose-Einstein distribution function, although with some deviation. Later on, we brought in some discussion on how to deal with the liquids, and there we talked about radial distribution function. With the discussion on radial distribution function, we then wanted to check how the scenario will be in the solid state. Due to the limited availability of time in this course, we could only restrict our discussion up to radial distribution function. For more advanced level of understanding, the further advanced level of statistical thermodynamics will be required. We started with an aim of understanding statistical thermodynamics, that means the link between individual molecular properties and bulk thermodynamic properties. We achieved the journey goal by first understanding molecular partition function, canonical partition function, then recovering molecular partition function from canonical partition function and connecting with all the thermodynamic quantities. So we discussed Gibbs free energy, Helmholtz free energy, enthalpy, pressure, heat capacity, internal energy, equilibrium constant. Once we have information about these thermodynamic quantities, then we have a complete characterization, rather thermodynamic characterization of the system under investigation. I hope this course was useful to you, with an understanding that all these thermodynamic quantities can be obtained by employing spectroscopy. Wish you all the best and thank you very much.